Before we go ahead and continue with the smoke on the ground, I just want to do a few things. So I'm going to show you one addition that I did to the setup, which is creating a collision field for the trees. And the way I did that was by basically bringing the points of the leaves. So if I go to my tree dynamics, you will remember that we had the out deform points. And what I'm doing is I'm bringing that merge here. So that's going to be the merge leaves. And then I'm just measuring their velocity and creating a VDV from particles with the settings that you can see in there. And I'm also using the velocity for the collision vel. So I have two fields, collision vel and collision. And I'm making the collision vel invisible, and then I'm caching everything. So this is what you have there. I'm bringing that collision field here, merging that field with everything else, and I'm just plugging that into my simulation. So what we have so far is very similar to what you saw in the previous video. It's just the trail of smoke. But the thing is that even though we are clamping everything outside this bounding box, if you look from the camera, we are still wasting a lot of data. Like, we don't really need all those voxels. And I just want this simulation to be faster. So what I'm gonna do is I'm gonna delete the density that's outside of the camera, similar to what we did with the Frustrum cool, where we were deleting points by the UVs based on the camera. So let me just go back in case you don't remember. If you go back to the ground dynamics, I think it was in some of the particle setups where, yeah, this one, we were basically creating an UV attribute from the camera, and then I was removing the geometry that was outside of the frustrum of the camera by using the UVs. I'm gonna actually update the path to relative now that I'm here. So I want to do that on the volumes. The problem is that volumes, we can't use the position of the volumes because we have voxels, right? So I'm gonna use something different in this case. And for that, I prepared another scene for you, which I have here. And it's basically a sphere, an animated sphere and an animated camera. So if I have a look at the sphere, you can see that the sphere, well, I have to look at the transform. The sphere is moving. And then I'm just measuring the velocity using a pyro source to create the attributes that I need, which in this case is temperature and density. I'm transferring the velocity of the original animation, and then I'm rasterizing those fields to create the fields that I need. In this case are density, temperature, and velocity. And then I have two dop networks. I'm gonna show you both options. And then I just have one camera that it's animated. So if I look from the outside, you will see that the camera is moving and the sphere is moving. So what I want to do is that as soon as the smoke gets outside of the camera view, it should be deleted. So I'm gonna show you the first option, and then I'll show you the other one. This one is just creating actually I don't need this subsolver. It's just creating a dop network, and then in there you can put the smoke object. In this case I'm using a sparse, and then I'm also using the pyrosolver sparse. And the parameters are just the usual thing. It's just that in this case, I'm not only visualizing density, but I'm also visualizing the velocity field. And I set the orientation plane to Y set. So what I'm gonna do is I'm gonna deactivate this volume wrangle where I'm doing everything. I'm gonna explain you in a minute what it does. And if I go ahead and simulate, what you will see is that as soon as the sphere starts moving, you get a trail of smoke. And you see that the velocity field remains there. So even though we are not seeing that smoke in the camera, the solver is still computing all those operations on the voxels that we are not seeing. There are operations that are quite heavy, like removing the divergence of the velocity field and then doing the projection back and then affecting the fields. It gets very slow the bigger this trail gets. So I just want to delete that trail. Just to show you a little bit more of the scene, this is just a normal volume source. I'm emitting density, temperature, and velocity. And I have an additional gas turbulence, which is doing nothing else than adding turbulence. And the pyro solver, I didn't modify anything. I just removed the buoyancy. That's it. I didn't do anything else. So I'm going to activate this gas field wrangle. I'll show you what the result is going to be, and then I'll explain what's going on. So you can see the camera here, and you can see that there's a diagonal line, which is basically the frustrum of the camera. You can imagine that there's the angle. And if I look from the camera, you can see that we are seeing all the way to the edge, but we are removing the density on the voxels that we don't need. And because there's an option, or basically the solver, it's deleting or removing everything when the density is lower than some value, which you can see if you go to the shape, and then dissipation will clump everything when density is below this value here. And because we are basically removing everything, once it finds that there's no density there, it's just gonna remove the other fields too. So I don't need to remove the velocity, for example. But what I'm doing here, it's similar to what we were doing with the UVs. It's just that I'm getting the position of each one of those voxels in camera space, and a function that lets you do that, it's 2ndc. So I'm gonna jump back one moment and I'll show you the same operation done with points. So I have a VDV from camera, and I'm creating that VDV just to compute a bounding box that contains the camera, and then from there I'm creating one volume, and that's it. If you look from the camera, you have one big volume there. Then I'm scattering some points. For now, I'm just gonna go back outside and I'll go into the view tab, and I'll make the icon of the camera a bit bigger so we can see it more clearly. Then what I'm doing in a point wrangle, I'm getting the position of the points. So I'm creating a string variable that is storing the path to the camera. You can see the path to the camera here. And then to NDC, it's gonna return the position of the points in camera space to the camera that you give it as an argument, as the first argument. And you also need to give it the position. And then it's gonna return another vector, which is the position of the points in camera space. So you can imagine that the camera is here. And then those positions are basically the positions in the camera space. If I look at the grid, you can see that they are starting from 0, and then they go all the way up to their distance from the camera. And because this is in camera space, you can do all sorts of operations in there. And then if you want to send them back to the original position, what you need to do is, rather than use to NDC, you use from NDC, and it's the same arguments. Basically need to give it the same arguments, and then you can see that there's no difference between the original position and this position. You can do operations here if you want. You can do calculations in the camera space by doing that. I'm just sending the positions of the points to the camera space so you can see visually what's happening. So let me show you with a volume. I have a VDV here, and then I'm running the same operation, but because from NDC it's gonna return something similar to what the camera UVs gave you before on the points. If you remember, we created that UV texture that was setting the UVs from the camera point of view. To NDC is gonna give you something similar. So if you compare the from NDC vector in X against some values like 0 and 1, you will get the same results that we were getting with the cooling from camera. Actually, if I set this to manual, and I'm gonna go very quickly to my other scene, and then if I dive inside the subnetwork where we are cooling by the camera, have a look at the wrangle. I'm just gonna copy this wrangle and I'm gonna paste it here. You can see that the operations are extremely similar between both of them. So on the points, I'm using the camera UVs, and on the volume, I'm using the from NDC. But the comparisons are exactly the same. I'm comparing against 0 and 1, and 0 and 1. What I can do also is create those offsets. So I'm gonna copy and paste those variables. So I'm gonna add again the X offset and the Y offset. And what I can do is here I could subtract minus X offset, and in here I could add plus X offset. I already explained this process with the points, so I'm not gonna explain it again. I'm sure you already understand this. And in here I'm just gonna subtract the Y offset, and in here I'll add the Y offset. So after I run that conditional, what I'm doing, if that condition happens to be true, is that I'm setting the density to 0 by multiplying it times 0. I'm just gonna close this point wrangle, and what you can see is that if I promote those values and then I go ahead and start modifying the offsets, of course you will need to go back into auto update, and you can see that we are basically setting an overscan for the volume. So what I'm gonna do is I'm just gonna do exactly the same as I've just shown you here, but I'm gonna use that inside our simulation. So let's go back to the spaceship fire and dive into the pyro solver. Oh yeah, and I actually forgot that too. So I'm just gonna go back here, and I shown you that we had a DOP network where I was basically doing that operation inside a gas field wrangle connected into the sourcing. So what I'm gonna do is that I'll do the same inside the pyro solver. So this is just a pyro solver wrapper. You can see that we had the same operation here. And if I dive inside, what I do is I have a volume wrangle connected to the source's output, and you can see that the code is exactly the same. So the process is the same. As long as you connect that wrangle to the sources, it should work. So let's go back to our scene. Here I have my pyro solver. I'm gonna dive in there, and then I'm gonna create a gas field wrangle, and I'm gonna copy the code that we just saw. And what I'm gonna do is create those parameters. So I'm gonna keep them as 0 for now. And this camera, I want it to be a path to the camera. So I'm gonna edit the parameter interface, and I'm gonna select that camera path, and I'm gonna swap it from string to an operator path. And once it's an operator path, I'm gonna set an op filter, and I'm gonna set it to camera only, and click accept. And then I'm gonna look for the camera. So now you have the camera in there. And additionally to the density, I also want to remove the temperature and the burn. And I'm gonna rename this wrangle to remove outside screen. And I'm just gonna go back up and I'll run a simulation. So I'm gonna run a simulation version 2, so later we can compare against. This simulation took around 1 hour, actually probably a little bit less, like 40 minutes or something like that. I'm just gonna measure how long it's gonna take after we modify those fields, and then I'll let you know how it goes and how fast it is. So I'll see you in 1 moment. Okay, so the simulation is done. This is version 1, the one that we had. This is version 2. You can see how much density it's being deleted, but if you look from the camera, you can see that it's looking correct. This simulation took 9 minutes, so it's actually much faster than what we had before, which means that I could increase the resolution a lot more now that it's not taking so long. I'm just gonna make a flipbook from the perspective. I just wanna see how much density we are actually deleting. So I'll make a flipbook by using version 1 and then another flipbook from the same perspective using version 2 just to compare them both. So I'll see you in 1 moment. Okay, so here we have 2 flipbooks. One is of the long one where we were just clamping the volume that went outside of the bounding box. You can see at the end there's a change in the volume. It's just because it was taking so long that I didn't cache the rest of it. I'm just gonna clamp the frame range to 1074 so you don't see that. And this was a fairly long simulation. It wasn't that bad. Like, I felt it was too long just because I was looking at the screen the whole time. But in general, what you do is you just send these simulations to the farm and then you work on something else in the meantime. Okay, and let's have a look at the other one. So you can see that whatever happens to be outside of the camera is just being deleted. And the simulation was much faster than the other one. Just because if you look, for example, at this frame and then you swap between the other frames, between the other flipbook and this one, you will see that almost half of the simulation, which is actually a bigger part than what we are actually seeing, it's being cooled, and that means that the simulation it's gonna be probably more than 2 times faster just by doing that simple trick inside the solver. So yeah, I just wanted to show you that. And then because you have less volume also in screen space, you're gonna be able to get more detail on your flipbooks, and you're gonna be able to definitely go to a higher resolution in the simulation. So now that we have that operation sorted, I'm gonna also use the same thing on the other smoke setup. So I'm just gonna keep that there, and then later I'm gonna come back and copy this node from here. Okay, so that's it from this video. I'm gonna carry on in the next one, creating the smoke on the environment. And then once we are done with that smoke, I'm gonna also create some sparks coming from the spaceship that are gonna be affected by the smoke. And then to end this sequence or this shot, what I'm gonna do is I'm gonna create some leaves coming from the trees that are going to be affected by the smoke. So I'll see you in the next video. Bye.